today our topic is differentiation on Riemannian manifolds. So, the question is, if we have some manifold which is embedded in an Euclidean space, then how can we take derivative or how we can do differentiation on that manifold. For example, if we have some let me say some sphere, we say this is some sphere, and then there is some let me say vector field on this sphere. There are some vectors over here. These can be in different manner. So, how can we take the derivative of this vector field on the surface of the sphere? Let me say if we have some cylindrical surface, and there is some vector field over the surface of cylinder. So, it can be in different manner. So, how can we take the rate of change of this vector field on the surface of the cylinder? Similarly, we can have a donut shape, a torus shape, and then the obvious question is how to take the, and there is some vector field over here. We say this vector field is represented by E, and how can I differentiate this vector field? So, in order to approach this problem, first of all we will do some simpler cases, and then we will finally reach to the differentiation of vector fields on any arbitrary manifold. So, now first of all we study vector field or differentiation of vector field on a curve. So, if we have some curve which is embedded in Euclidean space, let me also add this, embedded in Rn, n-dimensional Euclidean space. So, we have some curve, let me say this is some curve, and then there is some vector field over this curve. We say this is the vector field or this. Then how can I differentiate this vector field on this curve? So, here I am representing this vector field with Z. So, how can I take the derivative, or how can I find the rate of change of this vector field along this curve? Okay. So, to approach this problem, first of all I need to take the parametric representation of this curve. This is the curve, and for this I need to write the equation. So, this curve is represented by, let me say if we are in n dimension, then I can represent this curve as x of t, and this will become x1 t, x2 t up to xn t. So, these xi's are actually the coordinates of the n-dimensional space, and they are function of t parameter, which is a single parameter, and the graph of this equation will become a curve in n dimension. Now, if I am interested in the derivative of this curve, so that will become let me say I am interested in dx by dt. So, that will be the derivative of this curve with respect to the parameter t. So, I can represent this with x dot, can use this notation, and this will become derivative of the first coordinate, derivative of the second coordinate. This dot is representing derivative with respect to parameter t, and similarly up to this. So, what is dx by dt, or what is this derivative of this curve representing? So, actually this is representing the tangent vector along this curve. Let me say if we consider this point, so this dx by dt will be representing this vector which is tangent to this curve. But I am not only interested, this one is actually tangent to this curve. I am not interested only in the tangent fields. I am interested in arbitrary fields which can have any direction. So, I am interested in arbitrary vector fields and that means if I represent this vector field with z of t, which means z is the vector field and it is parameterized by this t variable. This zt can have tangential components as well as normal components. So, this is a general vector field along this curve, and I am interested to find the, I am interested to differentiate this vector field. Okay. So, let me redraw this curve over here. Let me say if this is the point which is parameterized by t naught and the vector field over here is z t naught, and let me take another point on this curve which is t naught, which is the position of this curve is t naught plus del t at this position. So, this is x of t naught, this is x of t naught plus del t, and at this position the curve that we are having, the vector field that we are having is let me say that is in this direction. So, now in order to find the derivative or differentiate this vector field, what I do that I find the difference vector del z. This will be also a vector which is obtained by z t naught plus del t minus z t naught. So, this will be the difference vector. Let me redraw it here. So, if I bring z t naught plus del t over here, so and then I subtract, so it will become like this. The opposite direction will become, it is in this direction. So, the opposite direction is this, and the resultant vector will be in this manner. This will be the del z vector. So, for differentiation purpose, I apply the normal procedure, and then this del z by del t will become 1 over del t z t naught z t naught. Now, if I take the limit, such that this del t tends to 0, and also here this del t tends to 0. Then this thing will become dz by dt. So, dz by dt is the differentiation of this vector field along this curve. So, this becomes limit del t tends to 0. So, now this dz by dt will have different components. This vector, which is the resultant vector, actually this del z or this dz by dt, this will be by itself a vector. This vector will have different components. So, we want to study this vector dz by dt. So, if I am having, let me say, if the unit vectors in this Rn are represented by this notation, the basis of Rn, if this is represented, let me say, by this set partial x1, partial x2 up to partial xn, then this dz by dt can be easily written in this manner. This will be actually a linear combination of all these basis vector. So, this will become ak and partial x k So, we can write this dz by dt in this manner. So, it will be a linear combination of all these basis unit vectors. Now, you can see that this formula, this is actually independent of the basis, and the resultant vector, which is this dz by dt, does not depend on the coordinate system that we use. We will get a specific vector from the differentiation of z vector field, and that will be independent of the basis in which we are representing it. So, now we take a very simple example of this, and we want to see how this concept works. So, let me say I am having this curve x of t is equal to cos t x cap plus sin t y cap in 2D in R2, very simple example. I can also write the same equation in this manner, cos t sin t, where it is understood that this cos t is actually with x cap, sin of t is with y cap. So, what is this curve representing in R2? This is actually representing a circle. So, this is representing a circle. This is x, this is y. And if I take derivative of this dx by dt, So let me call this z, because this dx by dt is now a vector field, and this will become minus sin t x cap plus cos t y cap, or I can write it also in this manner. Let me write this with zt, this notation. So what is this representing actually? It is representing a vector field on this curve. So you can see that, let me draw it, let me say that at t0 we are here, which means z times 0 will become, this will become 0 and this will become 1, which means that the vector field has y component only at time 0, which is here. Similarly, if t is equal to pi by 2, so at t is equal to pi by 2, this will become, zt will become minus 1 0, and which means minus x cap, which means the vector field is actually here, because it is in the minus x direction. And similarly you can plot it for other points as well. Here it will become like this, here it will become like this, here it will become like this. So this zt is a vector field on this curve. Now what will be the derivative of this vector field? dz by dt. So this will become minus cos t x cap minus sin t y cap, or you can write it also in this notation. Now you can verify this by yourself, that this is always perpendicular to z, which means the inner product of z and this dz by dt is 0, because they are perpendicular. You can check this. Let me take this dz by dt at t is equal to 0. So what I am getting is this minus 1 0, which means minus x cap. Now if I plot this here, so what will I obtain? The vector will come in this direction. So you can see that between this the angle is 90 degree, pi by 2. So they are perpendicular, so therefore their inner product is 0. You can do this for all points. For example, at t is equal to pi by 2, what will happen? This will become 0 minus 1, and if I plot it, this means minus y cap, and this means that at t is equal to pi by 2 I am here, and minus y cap means that this. So these two are again perpendicular to each other. So therefore the inner product of these two is 0, and you can also verify this by computing explicitly. Now this situation was quite simple, because the simplicity was due to the basis that we had chosen. Actually this basis that we have considered here, these are the normal Euclidean basis vectors, these, and these basis vectors actually do not change with the position. They are same with position, and they do not change with position. So therefore they do not give any complication when we are calculating the derivatives. So now when we go to the other vector fields, where we take a basis which is actually not constant. If we have a situation in which the basis vectors are not fixed and they are not in the same direction everywhere, So then the complication in the differentiation of the vector field will definitely increase. So up to this point we assumed that the basis vectors are actually in this manner. Basis was actually in this manner, partial x1 to partial xn, and these are fixed basis vectors which are not changing their direction with position. But sometimes it is convenient to change, to have a basis which is going along the curve. So for example, if we have this curve, so one is that fixed basis system. Let me say this is partial x1, this one is partial x2, this is partial x3. These are the normal basis vectors that we used for Euclidean spaces. But sometimes we prefer basis which is, for example, here it is in this manner, and once we shift here, then it becomes like this, and so the vectors, unit vectors or the basis vectors are changing their directions. So in such cases the differentiation will become a little difficult. So I call these basis vectors, represent them by f. Let me call this f1t, let me call this f2t, this one is f3t. These are frame vectors. So in this case the basis set will become, we say f1t up to fnt. So here now the basis is actually depending on t, because at different positions these basis vectors will have different direction. So now what will happen in such case, the vector zt will become equal to, we say this will become bkt and fkt. So here I am following Einstein's notation, and in this notation actually what is happening is that any summation which is taken, any index which is taken twice is actually the summation index. So now the derivative, as the basis vectors are also depending on t, so the derivative will become dz. Derivative of the vector field will become, you can also write this explicitly, summation is over k. So this will become dbk dt fkt plus bkt dfk dt. Now again this dfk by dt will be a vector, this part. This is the rate of change of this unit vector or basis vector, and this vector by itself will be a vector. The rate of change or dfk by dt by itself will be a vector, which will be again a linear combination of fi's. So I can write this in this manner, dfk by dt, which is only this part, will become AK I FIT. This is again summation over I, or you can use Einstein notation where the summation is over I. So now this dz by dt will become summation over k and again there is again a summation over AIK FIT. So this summation is over I. So now I don't use these summation symbols, instead I am following the Einstein's convention. So following Einstein convention we can simplify these expressions, because writing summation becomes difficult every time. If we follow Einstein's summation notation, so this will become dB. Let me, instead of k, I can also write L, because it is summation notation, summation index, FLT, and then BLT, and AI, and let me write this also L, AL, and let me write this. So BKT, I have replaced K with L, so BLT, and then AILT, and then FIT. Okay, I can take this FLT common. So to simplify this equation, so I should take this in order to simplify this, I should take this summation index and this summation index same, because it doesn't matter. So I will use M for this, dBm by dt FMT plus BLT AILT. So this is M, so FMT. So this dz by dt will become equal to, now I can take this common, so dBm by dt, and then plus BLT AMLT, and this becomes FMT will come here. So this is the final equation for the differentiation of the vector fields in the general frames which we have taken over the curve. So here the general unit vectors or basis vectors are actually from F1 to Fn. M is just a summation index over here. Now to see the applications of this differentiation, we are going to apply this concept on space curves and see what is happening over there. So geometry of space curves. or we can derive some useful formulas with the help of these equations, and these are called Frenet-Serret formulas. But before going that, you can see that if I have two vector fields, because these we will use these equations were there. Let me say if I have two vector fields z1 and z2 and I add them and then take the derivative. So it will be dz1 by dt, because derivative is a linear operator. Similarly, if I have this type of situation that I have some function over the curve and then this vector field is there. So df by dt multiplied by vector field to f of t dz by dt. And similarly, if I have the inner product of two vector fields, z1 inner product with vector field, and I take the derivative of this, this will become derivative of first inner product with second and plus first inner product with derivative of second. So these are some simpler properties. Derive the Frenet-Serret relations with the help of the above equations. Frenet-Serret relations. Okay, so let me say if we have some curve and we parameterize it with t, so this will become x of t. Now I can parameterize this curve also with the length of this arc, because you can see that this arc is having some, let me say this is the initial point, so then onward here will be some distance or length of the arc at each point. So let me say initially at this point the length is 0, and let me say here it is 1, here it is 2, here it is 3, here it is 4, here it is 5, and so on. So I can parameterize this curve with the help of this length s. S is the length or distance from the origin or from the initial point. S is here distance from the initial point. So each point can be uniquely labeled with this S, and so we can parameterize this curve with the help of S. Now in general this S is given by integration of ds, and we know that ds is given by, if we just think about two dimension, then this becomes dx square plus dy square root. In general, we can write this in this manner. If we generalize this, this becomes equal to integration and the inner product of x dot t with x dot t, then 1 by 2, and then integration of dt from some initial time to final time t. So this is the general formula, because this formula can be actually derived from this one, because this is nothing but for example, if I take this to be x of t as uh, let me take this bold x of t. So this is x of t, y of t. So in two-dimension case, I can write this in this manner. This s will become t naught to t, and this will become dx by dt dx by dt x cap plus dy by dt y cap, and its inner product with dx by dt x cap plus dy by dt y cap. So this is the situation. So I can write this, if I solve this. So I have dx by dt, also 1 by 2 is here. So dx by dt square plus dy by dt square, then 1 by 2 in dt is here. So this will become equal to dx square plus dy square. So you see that this is exactly same as this formula. 1 by 2 is also there. So in general, we write in n dimension. This becomes x dot t, its inner product with x dot t and dt. Now if I parameterize the curve with s, so if this is the curve, so then this will become x of s instead of x of t. I can parameterize the curve by any parameter. So then what will become? From this equation I can see that ds by dt is actually this x dot t, x dot t. So if parameterized by s, then that will means ds by ds will become equal to x dot s, x dot s, and this is definitely equal to 1. So this implies that x dot s is actually unit vector, because its dot product is 1. So let me call this unit vector the tangent vector. T, the function of x, will become dx by ds. X is a function of position, so dx by dx. Actually this x is representing the whole curve. So this is the tangent vector. Now if I take the derivative of this tangent vector, we call this vector tangent vector. If I take the derivative of this tangent vector, then what will happen? So this will become dt by ds, dt by ds. So this will be, we have seen that this vector is actually normal to the tangent vector. For example, in the case of circle, we have already seen that these two are actually perpendicular. In the case of circle, you can see that this is dt by ds. If this is t vector, then this one is dt by ds, and this is perpendicular to the tangent vector. You can also verify it in this manner that, for example, if we take the inner product of t and dt by ds, so we will obtain 0. So how can I do this? Let me say, because this ts is a unit vector, so I can take this ts and then ts, the inner product is 1, because this is a unit vector. So now I take derivative of both sides with respect to arc length, and I obtain this dt by ds is equal to 0, and this means 2 times ts, which means this thing is 0, and this actually implies that dt by ds is perpendicular to t. Now this dt by the magnitude of this dt by ds, magnitude of dt by ds, I call it, define it as a capice, and I call this curvature. So this is actually curvature. It shows the curvature, the amount of curvature in the curve, and this is also apparent from the geometry. If we have some curve and we take tangent vector on this, so the rate of change, for example, at this location here, the rate of change is in this direction. This dt by ds is actually in this direction, while here it is in this direction, here it is in this direction. So it shows the curvature. If you take some curve which is straight, so then what is happening, that its tangent vector is along this, and it is not changing, dt by ds is 0. So there is no curvature in this, the magnitude of this is 0. There is no curvature in this curve. So actually magnitude of dt ds is defined to be the curvature of the curve. And this is actually the extrinsic curvature. We will see the intrinsic curvature later on. Now we have also seen that this dt by ds will have a direction, and that direction is actually normal to the tangent vector, because we have verified here from this result that the curvature is dt by ds is normal to the t vector. So this means that this dt by ds can be written in this way. Its magnitude and its direction It will represent the direction by this. So I call this magnitude the curvature ks and dt by ds the normal vector. So this becomes the whole vector. So I get this expression ksn. dt by ds is equal to k into n, where n is perpendicular. So for example, if we have some curve and the tangent vector is in this direction, let me say in this direction, this is t, then normal vector will be here. So this will be the normal vector. It is perpendicular to the tangent vector, and dt by ds is actually in this direction. The rate of change of tangent vector is in the direction of normal vector. Now I have two vectors. In 3 dimension I need 3 vectors to specify everything. So I can take another vector which is perpendicular to both of them, and I call that binormal. Let me draw it with this color, with this yellow color. This is binormal. So if, let me say this is let me say if t is here and n is here, then b will be here. So this is called t and b. This is the binormal vector. Binormal vector is actually perpendicular to both t and n vector. So now if we know that this t and b will have, because the tangent vector, the remaining two are depending on this tangent vector. So if this tangent vector is changing with position, then definitely n and b will be also changing with position. So you can see that, let me say if t is here, then n will be somewhere perpendicular to this. Let me say if it is here, then b will be perpendicular to it, and then t has changed its direction, so n and b will also change its direction at this location. So so these are actually the frame basis vectors for this curve. So if we have some curve, let me say we have some curve over here, then at this location this will be t and b frame, at some other location this will be different. Maybe the more appropriate, if let me say that t is in this direction and then n is in this direction, so b will be out of the plane. So now we have, if I label these t and b is in the language of f, using f symbols, so I call this f1. f1 of s, this is defined as t of s, and f2 of s is defined as n of s, f3 of s is defined as binormal vector b of s. Now I know that all these three are actually perpendicular, so I can use this relation that FIS, inner product of FIS and FJS, is del ij. It means this is 1 if I is equal to j, 0 otherwise, because they are perpendicular. So the inner product of t and b, and similarly nb, bt, all of these will be 0. So now I take the derivative of both sides with respect to s, and I'm actually interested in finding some relations between them. And how can I do this? I can take the derivative of this inner product, because this is the expression in which different terms appear. So what will happen? This will become, if I take the derivative with respect to s of left hand side and right hand side, I obtain this dfi by ds fj plus fi dfj ds, and this is equal to 0. So now if I, this dfi ds, this will be actually a vector again, and this can be represented as a linear combination of let me say ak I s and fk. So it will be again a linear combination of these frames, because this dfi ds will lie somewhere over here. Let me say it is dfi by ds. So it will be again a linear combination of these three vectors, which are f1, f2 and f3. So again I can write this now in this manner: aki s fk fj plus fi, and similarly I can use akj s fk for this one also. This will also become a summation. I am using Einstein's notation over here. Again I am using this formula: fi inner product with fj is del ij. So using that notation, you can see that from this term I will obtain a ji s, because this will become del ij, and then I can replace it in this manner, and plus from this I will obtain ajis. So this will become aijs. So this will become aijs, and this is equal to 0. How I obtain this expression? Actually what is happening that we are taking the inner product of these fk fj. So this will give me 1 if and only if this k is equal to j. So this will make this k equal to j. And similarly, when I'm taking the inner product of this vector with this one, so this will give me del ki, which means this k will become equal to I, and as a result I will obtain aijs, and from here ajis. Okay, so this I and j will go from 1 to 3. So I and j will start from 1 and will go up to 3. Now, if you think of this as a matrix, because there will be different components, so this matrix will be in this manner: A11 S. So I don't write S every again and again. So this will become A12, A13, similarly A21, A22, and A23, and A31, A32, A33. So this is now the resultant matrix. Now what this equation is telling me, this equation is actually telling me that this term Aji and Aij, these are actually the antisymmetric terms. These are these off diagonal terms. For example, this is A12, so A21 is here. A13 is here, so A31 is here. And similarly A23 and A32. When we add these two terms, so they will give me 0. So this means they are just the negative of each other. If this one is plus 5, then this one will be minus 5. So this is an antisymmetric term matrix. So these results imply that the matrix is actually antisymmetric matrix. Okay, so now I will make use of these terms. So this directly means that some terms will become 0 and all these diagonal terms, all these terms which are lying actually at the diagonal, they will become 0. These terms will become 0 because antisymmetric terms matrix has 0 terms over here. So these terms will become, which means Aii, this will become equal to 0, which means A11, A22, A33, all of these terms will become equal to 0. So now what is happening, the next is this, that we have this thing. So we have this now we obtain the remaining terms and we want to see what are the remaining terms. As the matrix is antisymmetric, so A12 is same as A21 but with the opposite symbol, and similarly A13 will become minus A31 and A32 will become minus A23. So now let us see what I can obtain from these relations that I have over here. I have this expression over here. This expression, that dfi by ds is equal to AKIS FK, and I already know that dt by ds is actually equal to KSN. That means df1, because t is f1 actually, by ds is equal to KSN, and n is what? N is actually f2, and I have here A21. So from this equation, from here, this equation, so df1 by ds is equal to so if I take I as 1, so dt by ds, because f1 is t, and this will become A21 is f1, A21 f2. So this implies, because you know that df1 by ds is actually this, A11 f1 plus A12 A21 f2 A31 f3, And I know that this thing is 0 because of the antisymmetric matrix, and I also know that this is f1 is t, so dt by ds, and ksn, I know this expression, so n is this part, a21 is ks1, so this means a31 will become equal to 0. So a31, and that automatically means that a13 is also equal to 0. So this is the one relation that we have. Now similarly, if I go to the second expression, which is, let me go to the third expression, df3 by ds, and that means a13 f1 a23 f2 a33 f3. Now I know that from here that a13 is actually 0, and I also know that a33 is equal to 0. So this df3 by ds will become equal to a23 f2. There is no reason with me to make a23 is equal to 0. So I call this, I know that f2 is actually normal vector in a23. I call this a23 tau of s, and this f2 will become, f2 is actually the normal vector. This is the normal vector, and this f3 is actually the binormal vector. So this will become db by ds equal to, and if I take this a23 equal to minus tau of s, for some reason that will become apparent. So this is the equation, minus tau of s n. So this is the second relation that I obtained. And now finally I check what about df2 by ds. You know that this will become a12 f1 plus a22 f2 plus a32 f3. Now this f2 is actually normal, so dn by ds. I know that a12 from here is ks. a21 is ks, so a12 will become minus ks. So this will become minus ks, and this f1 is actually t. And I know that this a22 is equal to 0, and a32 is equal to, as this is a23 is minus tau s, so this will become equal to plus tau s because of antisymmetry. So this will become plus tau s, and f3 is binormal. So I have these relations which are called Frenet-Serret equations or relations, and they are finally dt by ds ksn, and then dn by ds minus ks t plus torsion of s to b, and then the dp by ds is equal to minus tau sn. So these are the relations which show how these frame vectors differentiate with the arc length and how they are interrelated with each other. Now what is this tau s physically? Physically this is actually the torsion. Tau of s is the representing the torsion of the curve. What is meant by the torsion? Then ks or kappa s is actually, this is the curvature. So for example, if we have this curve, so it will have some curvature over here. Let me say that this becomes straight over here. So the curvature in this area will become 0. But here the curvature vector will be in this direction. Curvature will be there, dt by ds. And here the curvature will be there, dt by ds will be also here. But if this curve is in a single plane, for example it is in the xy plane, then the torsion of this will become equal to 0, because this is completely in a single plane. So torsion actually measures that how much a curve deviates from a planar curve. So if a curve is in a single plane, then its torsion will be 0. Otherwise it will be having torsion, because you can see from this relation that it is related, torsion is actually related with the derivative of this vector, binormal vector. And if this binormal vector is actually constant as long as the curve is in a single plane. But if it is changing its plane, then this thing will not be constant and it will be giving some value of torsion. Okay, so we stop here.